Good morning, student. Today I am going to discuss about new unit crystal physics of physics 3. So we have to know that matter in universe is mainly classified into three kinds: solids, liquids and gases. So first of all you have to know that what do you mean by solids. All atoms or molecules are arranged in fixed manner and have definite shape and size. It's called a solid. Now liquid and gases means atoms or molecules are not fixed and cannot form any shape and size, and they gain the shape and size in the container. Now basically solids are classified into two categories. One is crystalline solids, another is amorphous solids. So what do you mean by crystalline solids? The solids in which atoms or molecules are arranged in regular and periodic manner in three-dimensional geometrical pattern are called as crystalline solids. And these solids have directional properties and called anisotropic substance. Example of crystalline solid, that is metallics, is gold, silver, aluminum. Non-metallics means diamond, silicon and sodium chloride. Second one, going to discuss about amorphous solids. Amorphous solids means atoms or molecule are arranged in a irregular manner. There is no lattice structure and the solids have no directional properties and are called an isotropic substance. Example: glass, plastic, rubber, etc. Now what is the difference between crystalline solids and amorphous solids? Crystalline solids, atoms or molecule have regular periodic arrangements. Amorphous solids, atoms or molecules are not arranged in a regular periodic manner. They have random arrangement. Crystalline solids exhibit different magnitudes of physical properties in different directions. But amorphous solids, they exhibit the same magnitudes of physical properties in different directions. Crystalline solids, they are anisotropic in nature. Amorphous solids, they are isotropic in nature. Crystalline solids exhibits directional properties, but amorphous solids, they do not exhibit directional properties. Crystalline solids, they have some melting points. Amorphous solids, they do not possess some melting points. Crystalline solids, that is, if you break a crystals along a regular crystal planes, and hence the crystal pieces have regular shape. Example: copper, silver, aluminum, etc. But in amorphous solids, if you to break into irregular shape due to lack of crystal planes, glass, plastic, rubber, etc. Now, it's important terms, lattice points. The points in the space replacing the atoms in the structure of a crystal with regular periodic arrangements and have identical environments with respect to other points are called lattice points, and this is called as lattice points in this figure. Primitive vectors, the vectors which when repeated regularly given the array of lattice points in space lattice, they are known as fundamental transitional vector or basis vector or primitive vector. In this figure here given some vector signs. Now space lattice or crystal lattice. The regular orderly arrangements of lattice points in space which resemble the atoms or molecule in a crystal such that every point has same environment with respect to all other points is known as space lattice or crystal lattice. So lattice basically the regular orderly arrangement of lattice points in space which resembles the atoms or molecules in a crystal such that every point has same environment with respect to all other points is known as space lattice, or it is also called as crystal lattice. So this crystal lattice is two-dimensional and three-dimensional. So two-dimensional space lattice means the regular orderly arrangement of lattice point in two-dimensional space which resembles the atoms or molecules in a crystal such that every point has same environment with respect to all other points is known as two-dimensional space lattice. Now, what do you mean by three-dimensional? So, three-dimensional space lattice means the regularly orderly arrangements of lattice points in three-dimensional space which resembles the atoms or molecules in a crystal such that every point has same environment with respect to all other points is known as three-dimensional space lattice. Now, what do you mean by basis? The set of atoms or molecules attached to each lattice point in a crystal structure, identical in composition, arrangements, and orientations, is called the basis of a crystal lattice. So, in these figures, here atoms or molecule here indicates and this is basis. So lattice plus basis you get the crystal's structure, and it is also known as each lattice point attached in an atom is called as basis. So this is very beautiful examples. This is basis plus lattice, and you have to find out the crystal structure. Now going to discuss about unit cell. The smallest block or geometrical figure from which the crystal is built up by the repetition in 3 dimensions is called unit cell, or the fundamental grouping of particles which are repeating entries is called unit cell. It is a fundamental elementary pattern. This unit cell is basic structural unit or building blocks of crystal structure. Unit cell basically 3-dimensional and 2-dimensional. Mark in figure also. Now fundamental types of lattice. Lattice can be found such that 1, 2, 3, 4 and 6 for rotation axis carry the lattice into itself corresponding to rotation by 2, 2 pi by 2, 2 pi by 3, 2 pi by 4 and 2 pi by 6 radian, and by integral multiple of this rotation. This rotation axis is denoted by 1, 2, 3 and 6. This is symbolically. But we cannot find a lattice that goes into itself under rotation such by 2 pi by 7 radian and 2 pi by 5 radian. Basically, a single molecules properly designed can have any degree of rotational symmetry, but an infinite periodic lattice cannot. We can make a crystal from molecule that individually have a 5-fold rotations and axis, but we should not expect the lattice to have 5-fold rotation. So in this figure we show that what happens if we try to construct a periodic lattice having 5-fold symmetry. The pentagon do not fit together to fill all space, showing that we cannot combine 5-fold point symmetry with the required in transitional periodicity. Two-dimensional lattice types. In this figure, we drawn an arbitrary, that is A1 and A2, a general lattice, as this is known as aequic lattice, and is invariant under rotation of 2 pi about any lattice points. But special lattice of the aequic types can be invariant under rotation of 2 pi by 3, 2 pi by 4 and 2 pi by 6 under mirror reflection. We must impose restrictive condition on A1 and A2 if we want to construct a lattice that will be invariant under one or more these new operations, and these are 4 distinct types restrictions, and each leads to what we may call as special lattice types. Thus, there are 5 distinct lattice types in 2 dimensions and the oblique lattice of the 4 special lattice. In this figure, so Bravo lattice is the common phase for a distinct lattice types. We say that there are 5 Bravo lattice in 2 dimensions. 3-dimensional lattice types. The point symmetry groups in 3-dimensional require the 14 different lattice types listed in this table. The general lattice is triclinic, and there are 13 special lattice. These are grouped to convenience into system classified according to 7 types of cell, which are triclinic, monoclinic, orthorhombic, tetragonal, cubic, trigonal and hexagonal. So first is crystal structure cubic, lattice parameter alpha A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degree. Second one, tetragonal. Tetragonal is A not equal to A equal to B not equal to C and alpha equal to beta equal to gamma equal to 90 degree. Orthorhombics, A not equal to B not equal to C and alpha equal to beta equal to gamma equal to 90 degree. Monoclinic, A not equal to B not equal to C and alpha equal to beta equal to 90 degree and gamma not equal to 90 degree. Triclinic, A not equal to B not equal to C and alpha not equal to beta not equal to gamma not equal to 90 degree. Rhombohedral, that is trigonal. Trigonal means A not equal to B, A equal to B equal to C and alpha equal to beta equal to gamma not equal to 90 degree. Hexagonal, A equal to B not equal to C and alpha equal to beta equal to 90 degree and gamma 120 degree. Now crystallographic axis. These are the lines drawn parallel to the lines of intersection of any 3 faces of the unit cell which do not lie in the same plane OX, OY and OZ. Primitives. The 3 sides of unit cells are called primitives. It is denoted by A, B, C and they are also known as lattice constant. They are also called lattice constant. Interfacial angles. The angles between three crystallographic axes of the unit cells are called interfacial angles. That is, in this figure, now I am showing about angle between y and z is alpha, angle between z and x axis is beta, and x and y axis is gamma. So ABC, you have to know that primitives, and alpha, beta, gamma is interfacial angles. Bravais lattice in 1948, Bravais shows that there are 14 ways of arranging points in space lattice. Under the 7 crystal systems, to describe a crystal, they are classified on the basis of the following crystal lattice. Primitive lattice. In this lattice, the unit cells consist of 8 corner atoms, and all these corner atoms contribute only one effective atoms of the lattice. So basically primitive lattice means you have to take the just a cube. In cube there are 8 corner, and in 8 corner you have to situate 8 corner atoms, and only one effective atoms of the lattice is contributes. Body center cubes or body center lattice. In this lattice, in addition to the 8 corner atoms, it consists of one complete atom at the center. Face center lattice. In this lattice, along with the corner atoms, each face will have one center atoms. Base center lattice. In this lattice, along with the corner atoms and base and opposite face will have the center atoms. So this is simple cubic, body center cubics and face center cubics. Simple cubic means 8 corner right atoms. Body center cubics is 8 corner right atoms and one of the center of the body, and face center is 8 corner of 8 atoms, and every faces have one atoms, that is 6 faces is 6 atoms. Crystal systems or Bravais lattice. So before also I am discussed about this 7 types of lattice. So basically you have to know that body center, 4 types unit cell, primitive, body center, face center and side center, plus 7 crystal classes, that is all is 14 types Bravais lattice. Now expression for lattice constant. In a cubic unit cell, the side of the cube are equal and constants which are known as lattice constant. A equal to B equal to C, this is called as lattice constant. Suppose a cube unit cell with lattice parameter is A equal to B equal to C and alpha equal to beta equal to gamma 90 degree. Suppose rho be the density of the cell. So mass of the cubic unit cell is AQ rho. You have to take equation 1. If m is the molecular weight of the cell and n node A is the Avogadro's number, so mass of each atoms in unit cell m by n. If small n is the number of atoms in unit cell, then mass of the cubic cell is small n m by na. You have to know that na is the Avogadro's number. This is take as equation 2. From equation 1 and 2, you have to know that AQ rho equal to Nm by Na. So AQ equal to Nm by rho capital N. And this A equal to, you have to find A equal to bracket start Nm by rho Nm bracket close 1/3. Now important definitions, atomic radius. So atomic radius means the half of the distance between any two successive atoms in a crystal's lattice is called atomic radius. Nearest neighbor distance. The distance between two nearest neighbor atoms in a crystal lattice is known as the nearest neighbor distance. Effective number of atoms per unit cell. The total number of atoms in a unit cell by considering the contribution of corner atoms, center atoms and face center atoms is called effective number of atoms per unit cell. Coordination number. Coordination number, it is denoted by capital N. The number of equidistant neighbors that an atoms has in a crystal lattice is known as coordination number. Coordination number of simple cubic is 6, body center cubic is 8 and face center cubic is 12. Atomic packing factors. Atomic packing factor basically the ratio between total volume occupied by atoms in a unit cell divided by volume of the unit cell, or the number of atoms present in a unit cell multiplied by volume of the one atoms divided by volume of the unit cell. Intertrial space or void space. The empty space available in a crystal lattice with atoms occupying their respective positions is called intertrial space or void space. So density, you have to know that AQ equal to Nm by rho n, or rho equal to small nm by AQ rho Na. You have to know that Na means Avogadro's number, or small is the number of atoms. In a simple cubic crystal structure, a simple cubic unit structure consists of 8 corner atoms, and it is a primitive cell. And lattice parameter in simple cubic hypothetically A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degree. Now effective number of atoms in a unit cell. So in actual crystals, each and every corner atoms is shared by 8 adjustment unit cell, and there are each and every corner atoms contribute 1 by 8 of its part to the one unit cell. Hence, effective number of atoms in a unit cell 1 by 8 into 8, that is number of atoms per unit cell in simple cubic structure is only 1. Nearest neighbor distance, let R be the radius of the spherical corner atoms, then the nearest neighbor distance 2R, that is 2 atoms, radius 1 is R plus R, totals 2R, that is A. Now coordination number for corner atoms, there are 4 nearest neighbors in its own plane, and there is one nearest neighbors in a plane which lies just above these atoms, and yet another nearest neighbors is another plane which lies just below these atoms. Therefore the total number of nearest neighbor is 6, that is coordination number of simple cubic structure is 6. Atomic packing factors. A corner atom is shared by 8 unit cell. Contribution of a corner atoms is 1 by 8. Cube has 8 corners. Hence, contribution of 8 corner atoms is 1 by 8 multiplied by 8, that is only 1. So, number of atoms per unit cell in simple cubic is 1. If R is the radius of the atoms, distance between the center of two neighboring atoms, that is 2R equal to A, r equal to a by 2. So volume of one atom is equal to 4 by 3 pi r cube, or volume of the unit cell equal to a cube. So atomic packing factor equal to total volume by atoms in a unit cell by volume of the unit cell. That is, total volume occupied by the unit cell equal to 1 into 4 by 3 per r cube divided by a cube. So that is 4 by 3 per r cubes. A value you have to know that a equal to 2 r cube. So after solving you get that pi by 6, and this pi by 6 value equal to atomic packing factor equal to 0.52, or that is 52% volume of the simple cubic cell occupied by the atoms. Example, polonium crystals. Hence this structure is loosely packed. So three-dimensional viewing showing the number of atoms per unit cell, simple cubic, body center cubics, and face center cubic. Body center structure. Body center cubic structure consists of 8 corner atoms and one body center atoms. It is not a primitive cell. The lattice parameter A equal to B equal to C and alpha equal to beta equal to gamma 90 degree. Now effective number of atoms in a unit cell. In BCC, unit cell, each and every corner atoms is shared by 8 adjacent unit cell. So total number of atoms contributed by corner atoms 1 by 8 into 8 equal to 1. So BCC unit cell has one full atoms at the center of the unit cell. So the effective number of atoms present in a BCC unit cell 1 plus 1 equal to 2. So number of atoms per unit cell in body center cubic structure equal to 2. Now coordination number, the nearest neighbors for a body center atoms is a corner atoms. The body center atoms is surrounded by 8 corner atoms. Therefore the coordination number of BCC unit cell is 8. Atomic radius for BCC, the atoms touch along the body diagonal. So the diagonal length 4r. This is the 2r and there are two side r, so total 4r. From triangle ABC, in this figure you have to mark the triangle ABC. BC side is A and AB equal to A, so AC you have to find a square plus a square root over, that is root 2a according to Pythagoras formula. Similarly triangle you have to take ACD. ACD means AD square equal to AC square plus CD square. AC square you have to find 2a square, CD square a square means 3a square. So AD you have to find root 3a. So therefore root 3a equal to 4r. Total had 4r. So r equal to root 3 by 4. Root 3 by 4. So packing factors, total volume occupied by atoms in unit cells by volume of the unit cell. That is, in body center cubic, number of atoms per unit cell equal to 2 and volume occupied in a unit cell 4 by 3 per r cubes divided by a cube. So that is 8 pi r cube and 3 into, you have to know that r value equal to, a value equal to 4 by 3, 4 by root 3 r into cube. So packing factor equal to root 3 by 8 into pi means 0.68. So atoms in BCC occupy 68% in space, rest the empty. And BCC is tightly packed than simple cubic structure. And here void space is, or intertwined space is 32%. Example, sodium, potassium, chromium, tungsten, etc. Face center cubic structure. So face center cubic unit structure consists of 8 corner atoms, and each face has a center atoms. Lattice parameters A equal to B equal to C and alpha equal to beta equal to gamma 90 degree. Effective number of atoms in unit cell. Each unit cell consists of 1 by 8 into 8 corner atoms plus 1 by 2 into 6 face atoms. So total 1 by 1 plus 3 equal to 4 atoms. So number of atoms per unit cell in face center cubic equal to 4. So to fit the same size sphere along the face diagonal must 4 atoms at the radius of the sphere. So you have to know that d equal to 4r. From Pythagoras face diagonal, d square equal to a square plus a square, that is d equal to root 2a. So hence d equal to root 2a means root 2, that is 4r, and r equal to root 2 by 4 into a. Coordination number for corner atoms, there are 4 face center atoms, and these face center atoms are its nearest neighbors. In a plane just above these corner atoms, it has 4 more face center atoms. In a plane which lies just below this corner, it has just 4 more face center atoms. Therefore, the nearest number of atoms is 12. So 1/8 of the atoms here and 1/2 of the atoms. Packing factors, each unit cell contains 1 by 8 into 8 corner atoms, 1 by 2 into 6 face atoms. So total number of atoms per unit cell equal to 4. Here B equal to 4r. So B equal to, you have to find A by root 2. So A by root 2 equal to 4r. So A equal to 4 by root 2 into r, or 2 root 2 r. So volume of the atoms in the cell 4 into 4 by 3 pi r cube, that is 16 by 3 pi r cube. So volume of a cube equal to a cube. So 2 root 2 r cube means 16 root 2 r cube. So packing factor, volume of the atoms by volume of the cube. So volume of the atoms 16 by 3 pi r cube divided by volume of the cube means 16 root 2 r cube. So you have to find pi by 3 root 2. After solving you get 0.74 means 74% packing factor of body center cubic. And example is nickel, silver, gold, copper and aluminum. Now one of the example is discuss about structure of diamond. You have to also familiar in diamond. So diamond unit cell is cubic. The unit cell has 8 atoms. This cubic structure of diamond is obtained by interpretation of 2 FCC sublattice along the body diagonal by 1/4 of the cubic edge. If X is one sublattice, has its origin at 0, 0, 0. Other sublattice Y has its origin 1/4 of A along the body diagonal A by 4, A by 4, A by 4. So each atom has 4 bonds, hence coordination number is 4. Fraction represents 1 by 4, 1 by 2 and 3 by 4 at the height above the base units of the cube edge. In unit cell, diamond has 8 corner atoms, 6 face center atoms, 4 more atoms located insides. So number of atoms per unit cell. In diamond, there are 2 FCC lattice. The effective number of atoms per unit cell of BCC lattice is each unit cell contain 1 by 8 into 8 corner atoms plus 1 by 2 into 6 face atoms. So total number of atoms per unit cell equal to 4. and 2 FCC unit cell 4 plus 4 8 atoms, hence effective number of atoms per unit cell in diamond is 8. Atomic radius, let one sub lattice is x and other is y is 1/4 away along the body diagonal. Consider the projection of atom y onto the bottom surface at z and joining x with z and to the edge of the cube xz square, that is a by 4 का square plus a by 4 का square, that is a square by 8, and xy square equal to xz square plus zy square, a square by 8 plus a square by 16, that is 3 square by 16. But xy square equal to 2r whole square, that is 4r square. 4r square equal to 3 square by 16, then you get r equal to root 3 by 8 into a. So packing factor, total volume occupied by the atoms in a unit cell by volume of the unit cell. So diamond has number of atom per unit cell 8 into 4 by 3 per r cube divided by a cube, that is you get it after solving 0.34 and 34%, and here void space is 66%. Examples: semiconductor, germanium, silicon possesses this structure. Now going to discuss about Miller indices, or it is also known as crystal planes. Miller indices are 3 smallest integers which have the same ratio as the reciprocal of the intercepts of the crystal planes with the coordinate axis. There are set of 3 integers used to describe the orientation of the crystal planes. So procedure to find the Miller indices: first, the intercept made by the crystal plane along x, y and z axis in terms of lattice parameter ABC are noted. ABC are noted. Second one, the intercepts are expressed as multiple of ABC. Third one, the reciprocal of the intercept are taken. Fourth, the reciprocal of intercept, the reciprocal are converted into integral by multiple of each one of them with their LCM. Fifth one, the integer are enclosed in a small parenthesis which represent the Miller indices of the crystal plane. Let the intercept by a given lattice plane on the 3 crystallographic axes x, y, z in the ratio PA, QB, RC, where A, B and C are primitive, P, Q are the small integers. This reciprocal of P, Q, R have taken 1 by P, 1 by Q, 1 by R. Find smallest integers HKL such that HKL equal to H is to K is to L equal to 1 by P is to 1 by Q is to 1 by R, and the set of integer HKL is called Miller indices. Example: let the planes ABC has intercept of 2 unit along x-axis, 3 unit along y-axis, 2 unit along z-axis. Intercept value are 2, 3, 2. Reciprocal of the intercept first is 1 by 2, 1 by 3, 1 by 2. Now smallest whole number is 6 by 2, 6 by 3 and 6 by 2. So note, while writing Miller indices, a comma or dot between any two numbers may be avoided. The positive x-axis is represented at 1, 0, 0, y-axis is 0, 1, 0, z-axis is 0, 0, 1. The negative x-axis is 1, 0, 0, negative y-axis is 0, 1, 0, and negative z-axis is 0, 0, 1. Important features: Miller indices represent the orientation of crystal plane in a crystal lattice. Any plane parallel to one of these coordinate axes will have infinite intercepts and the corresponding Miller indices becomes 0. A plane passing through the origins is defined in terms of a parallel plane having non-zero intercepts. If Miller indices of the plane have the same ratio, then the plane are parallel to each other. Example 2, 1, 1 and 4, 2, 2. If a plane is parallel to any axis, its fractional intercept is taken as infinity. Hence, corresponding index is 0. If a plane quotes a negative y-axis, if a plane quotes a negative axis, the corresponding index is negative. Cubic system direction HKL is always perpendicular to the plane HKL. The plane NH, NK, NL are parallel to HKL and have 1 by nth spacing. So here given the 0, 1, 1 means z axis is 1. Here x axis is also 1, positive x axis, and positive y axis also 1, and 1, 1 plane x1 and z1. So figure here given the indicates. So this is 0, 1, 0, and z axis given, y axis 0, 0, 1 means z1, 1, and y1 1 complement 0, 0, 2, 0, 0. Space between the lattice planes, distance of separation HKL plane. Let OA, OB, OC be the orthogonal axes. Consider a plane ABC with MI HKL passing through origin. Let ON equal to D is the normal to the plane ABC, which is the interpolar spacing for another plane XYZ. Let XYZ makes intercept A by H, B by K, C by L along 3 axes. Let alpha, beta and gamma be the angles made by the normal to XYZ axis. So cos alpha equal to D by OA, that is D by A by H means DH by A. Similarly, cos beta equal to DK by B. Cos gamma equal to DL by C. From this law of directional cosine, cos square alpha, cos square beta plus cos square gamma equal to 1. So cos alpha you have to know as DH by A का whole square, DK by B का whole square, DL by C का square equal to 1. So if you take the common D square, bracket start H by A का whole square plus K by B का whole square plus 1 by L by C का square equal to 1. For cubic lattice A equal to B equal to C, so D square H by A का square plus K by A का square plus L by A का square equal to 1, or D square by A square equal to, you have to find 1 by A square plus K square plus L square, or D by A equal to root over 1 by A square plus K square plus L square, or D equal to A by root over A square plus K square plus L square. So today's lecture is finished. Thank you.